Hi guys, welcome to the Hacker Hour on Quantum Computing. Sorry it's an hour later than usual. I should have had R&D work to do, but didn't. So just sort of generally, this is the outline of the talk. So this is an intro. I'm not going to go into the physics because I don't know it. I could have gone into the math or complexity theory, but I didn't have the time to read like 40 billion papers. So sometimes the answers will not be very technical towards the start, and then when I say some math, they'll start getting really technical. But this is roughly what I'll do. So first I'm going to just introduce the two big concepts in quantum computing, then just show you what research is doing about it. Then I'm going to show superposition with all its math, and then I'm going to start demoing IBM's kit so that you guys can start playing with it.
What if we don't want to play with it?
Well, you can, right? So, or you cannot. But you'll have the ability.
Talk a little louder.
Oh, okay. Anyway, so yeah, that's the talk. Oh, that sucks. All right, the citations didn't render. But so what is quantum computing? Why did this video? So to a child, they explained it really simply as, if you look at a bit, you can think of it as a coin being heads or tails, right? 1 or 0. But with a quantum computer, you can also rotate the coin. That's sort of the difference. So like it being like half rotated would be some sort of like superposition, which is an explanation. But the better explanation is to the teenager, which is superposition is like trying to guess if a coin is heads or tails while it's spinning. So that's like the probability distribution and things like that. That's where all the probability comes in. We'll see some of it, but not much. And then entanglement is when two coins are like locked into the same state. Entanglement's really cool, but we don't have sort of enough technology to sort of do it yet, because you need to entangle the quantum bits and then move them, and doing that safely is really hard because quantum computers are massive right now. But yeah, so superposition and entanglement are the two big buzzwords. Superposition means there's some probability attached to the state, so it's not necessarily a 0 or 1, and that's relevant because we can actually compute in terms of these probabilistic states. And then entanglement is two things are locked and will stay to the same state. Any questions already? Comments, concerns, criticisms because I can't get citations right? Okay. Good. All right. So before I go into like the math, so a couple big applications of this are fast factoring. So the whole it can break RSA like sort of meme, which also isn't that big of a deal because the crypto people are like one step ahead of that. Then you can do computational biology, or at least they're hoping to if they get quantum computers that are big enough. So the idea is, instead of doing protein folding on big computer models, you'll do protein folding on literal representations of proteins at the quantum level. And just briefly, what protein folding is like a way to model biology, so we better understand sort of how like cancer develops, and then we can develop a cure because we understand it. So that's the thing. Quantum machine learning is sort of similar because you can have multiple states. You can have your learning algorithm like encapsulate all its possible states instead of storing them. So instead of storing multiple bits to represent the state, it can just have one bit, which is probably what the state should be. And then yeah, there's some cryptography applications too. But point is, it makes things go fast. And so there's some craziness here because so when we started measuring computers historically, to measure the benefit, we started wondering, how do we do it independently of basic instructions? And that's what complexity theory is all about, which is why you learn big O in 111 and things like that. And the foundational equivalent here is quantum complexity theory, where we start reasoning about what are the basic quantum operators, and how many of them do we have to use. So we have big O, but for quantum things. There's a proof that you don't get multiple exponentials. So if an algorithm is in a classical computer is 2 to the n, the best you can do on a quantum computer is n. They have some sort of proof of that. And just because that's the best you can do doesn't mean that necessarily exists either. This is just sort of a lower bound. So like for example, I was showing people papers where for circuit satisfiability, the classical computer algorithm has some sort of formula like this. Don't get scared. It's not important. I'm just kind of doing this for a demo. Right? So this is classical. And then the quantum does something like this, where this log term comes into account for the error in the quantum computer. But the entire point is I get to pick up a whole square root here, which makes it faster. So that's the rough reason why people really care about quantum computers, because circuit satisfiability is like the hardest, or a baseline for the hardest problems we can try to solve nowadays. And this just shows you that quantum computers make them faster.
Can you explain where that comes from one more time?
What do you mean where it comes from?
The square root and why?
I'll sort of hopefully get into that, but it's essentially what will happen. I'll show you an example where basically, because if you have a function that takes in zeros and ones, so you take a 1, you put it somewhere else, and 0, right? You have some sort of function like this. The square root comes in from the fact that if I give it a state that's a probability distribution here, I can do it by I can give it one input instead of calling it twice and still get the same results out. I'll do this more rigorously in an example if I have time, but that's sort of where that square root comes in from, because I'm halving the number of times I call the function, but that number of times I call the function is in an exponent somewhere, so it puts a square root. Sorry, yeah, it's not like, it's kind of hand-wavy because honestly knowing both of these is just really challenging and not stuff that I want to focus on. The key point here being this is faster than this by a whole lot, and that's why we care about quantum computers. Any questions, concerns, comments? Heman, you don't know complexity theory? Okay, no? I don't. Yeah, the last important point, because this was sort of an interesting news article I got to read in like September, is one of the other problems in complexity theory is how do you know if a quantum computer even did any quantum operations? I just think it's interesting that people are even asking that question, because it is kind of hard, right? If somebody gives you a computer and says, make it do a thing and then tell me if it's a quantum computer, like how are you going to do it? What if the quantum computer was written to fake it, right? So there's a whole paper on that. A grad student did it literally in September. So now we can tell if a quantum computer actually did quantum stuff, because a lot of the time quantum computers will do stuff that computers normally can. So that was a type of question people were asking at some point. So it's just kind of interesting. But of course, we're actually at a very interesting point in quantum computers, because there are more open questions than I think we can even close in like lifetimes. So the first question is, of course, how to implement anything. Even these algorithms that they've theorized, we don't have the power to implement. So on a computer right now, quantum computer that physically exists, we can do 5 qubits. But most of these algorithms, and even to outperform a computer that we have nowadays, you need about 50. So you can say we're 10% there, but that's also like not a good measure at all, because it just gets harder and harder as you get more and more qubits. So, yeah.
Can we apply Moore's law to quantum computers?
Not yet, because they haven't, like, there's not as much adoption or pickup, and that's sort of why it doesn't come up. We also, I don't think we know enough.
Huh?
I don't think we even know enough yet, because we have these theoretical bounds, but we don't know like what adoption of quantum computers is going to look like and things like that. And Moore's law is like heavily influenced by the fact that businesses bought computers, right? Yeah, so that's one thing. We don't know how to implement anything. Second thing is, the best programming languages we have right now are like these really ugly assembly languages. There's not even like a C or like C's grandfather for quantum computers. So that's something I might hope to do one day, which is make a programming language for them. And then, of course, how do we even scale them? Because there's like a lot of physics questions there. Right now, also, quantum computers operate at such low temperatures that you literally need an entire room to store one, and the power consumption is like obscene and things like that. So most businesses don't yet have a use case for it. So you know, we have a lot of digging to do even without going into crazy complexity theory. But yeah, so there are a lot of open questions. And with that, I think I'm basically ready to go into the math. So before I do that, any concerns, comments? So
How are quantum computers implemented if they can be right now?
how are they implemented?
Yeah.
I don't know too much about this because it's mostly, there's something about microwaves because I heard once somebody in a quantum talk about microwaves, and I have no idea what she was on about. There's something about a millionth of a Kelvin, which is how cold it has to be at the bottom. So right now, if you actually look at a physical quantum computer, it's, I don't know, it's like hilarious because it looks like this kind of a shape. And then at the bottom here, there's like this really thin thing. And the entire idea is all of these are cooling layers. And over here, you're at like a millionth of a Kelvin. And that's where all the quantum effects happen that we can measure. So the entire idea is,
How do you measure those quantum bits? Because like, since it's in a superposition, it could shift either way for like a fraction of a second. So how do you measure that?
that's actually the entire point. So if you have a quantum bit that's in like perfect superposition and then you measure it, it's like uniformly random between 0 and 1. So like when you measure it, yes, that's it. It just happens like that. Yes. So if I get to the example, I'll show you how you can take something in crazy superposition and then like, depending on what it actually was or which, because actually I'll just get there and then maybe I'll comment on it then.
One more question. Can this square root bound, is there like some actual insight that we can derive in terms of NP complete problems just by, you know, lowering the compute time like this, or no?
I don't know. I'll be really honest. Can we drive any? Yeah, I don't think. I haven't read about it at all, so I can't comment on that at all.
Who's making the quantum computers?
Oh, who's making them? IBM's definitely making them. They're also making the open source kit that I'm going to demo, hopefully. Then Google is looking into some of them. There's a company called, I forget if they were bought out, but then there's like Deep Blue and D-Wave, which are two companies that existed at some point. I haven't heard about them. And I'm sure there's also like some, I think they were like government contractors, so they probably still exist. But yeah, so those 4 people are the biggest players in this field. Yeah. I mean, other companies also care, so like Microsoft is trying to have an SDK for it. So a lot of the presentation is actually based on a Microsoft research talk, so they definitely care. But I don't think they're actually putting out any hardware related to it. Ooh, wow, my computer's also falling asleep. Okay. So, and the last question before I go into math. Yeah, I get to do my stuff. All right. So this is literally why I use tech. So I'm going to start out by explaining a different way of thinking about classical computing. That's sort of what the first 3-4 slides will focus on, and then we'll go to quantum. So a way to represent classical bits is you can sort of think of them as their own axes. So this is going to be the 0 axis, this is going to be the 1 axis, right? And then if I move 1 unit along it, right? Over here it's a 0 bit, and over here it's a 1 bit. Right? Actually, oops, I answered my own question. Actually, let me get there. So we use vectors because they're easy to do linear algebra with. So when we do 1, 0, we're just moving along x once, and that's the 0 bit. We also write it in Dirac notation because we're pretending to be physicists, so there's a 0. I'll get to more about Dirac notation a little later. But does anybody want to guess how to represent a 1 bit? Also, you have sort of a hint here. Guess I'll write that. This is 1, 0. Anyone?
Wait, can you explain that graph one more time? Picture?
So this is sort of another way of looking at bits. So the way I'm going to look at bits now is if I'm moving along the x-axis, I'm moving sort of in the 0 direction. If I'm moving along the y-axis, I'm moving in the 1 direction. And so. Oh, okay, sure. So yeah, so moving along 1 unit in the 0 direction is a 0 bit. Moving along 1 unit in the 1 direction is a 1 bit. Does that make sense? Okay.
But does that graph only have quadrant 1, or are there like?
I mean,
negative?
so in a classical computer, you only have these two. We'll get to the rest of the quadrants when we go quantum. You had a.
Is it going to be 0 and 1?
Yeah. 0 and 1, and that's the first bracket I've written in my life, so hell yeah. But yeah, so in Dirac notation, it's a 1. Actually, I think I have a summary next slide. So yeah, this is a summary of how to denote classical bits in sort of quantum notation. It gets important pretty soon, but just a quick mnemonic to flip back and forth between these two is that the number in here gives you sort of the index of the 1 in the vector. And another thing to note is also the magnitude of the vector will always be 1. If you don't know what magnitude is, that means basically there will only be 1, 1. And we'll get to actual definition of magnitude later on, so you'll see that. Any questions so far? Everyone good with 1 bit? So then the next immediate thing is, what can I do on a bit? There are actually only 4 things I can do to a bit. Nothing, flip it, always set it to 0, and set it to 1. And if you do matrix vector multiplication, you kind of just get that these work. I don't know, are people good with linear algebra? Otherwise, I'll just walk through these. Literally, just anyone need me to walk through these, because it only gets harder from here.
No, please walk through them.
Okay. Do I have to write out like all 8 things? I don't know, we'll see. Yeah, I'll just do all the operations on the 1 bit to start with, and then if people are still confused, I'll do it on the 0 bit, and then hopefully it'll make sense by then. So I think everyone knows how the identity matrix works though, right? So when I do this matrix vector product, actually I'm gonna try something fancy here. This is totally not gonna work. Okay. It'll just, if I had 2 different colors, this would look less like nonsense. Right, so I'm just matrix vector multiplying here, like you do in 250. If you haven't done 250 yet, like you will do in 250, which is I take these 2, and if you just follow my fingers, I do this. So I multiply here, and then I add, and I multiply here. Right, so this 0 times this 1 plus this 1 times that 0. That's what's going on there. Everyone follows that, right? Okay, then I'll just 1, and then when I evaluate, what? Yeah, I get 0, 1. Sorry, there's zeros in different places, just threw me off. And now if I do the negation, I'm just gonna, basically you just literally get these 2 terms flipped, right? So
Shouldn't that be a 0 on the top?
That should be a 0.
that was supposed to be a 0.
Yeah.
My handwriting is also bad, so it might be a handwriting mistake.
So what's the first operation supposed to do?
This is identity. I'm just gonna write as ID, and then this is negation. So it'll take the 1 bit make it 0. Yeah.
Is it supposed to be continuous? Like, is this just a discrete subspace of a continuous like thingy?
Yes, we'll get there soon. And don't worry, there are 2 more dimensions. It's all good. It's all crazy math, man. 0, 1. Yes, everyone follows this much. And then, I don't know, I think I'll do the classic math professor thing where I'll talk at the board a lot if you make me do more computation. So just let me know if I'm like obstructing your view or like anything like that. But so far so good. The other 2 are like, Yeah, well,
Yeah.
yeah. If everyone's good, I'll just move on, actually, sure, because there's more exciting stuff. And honestly, you might need more time there. I guess I can come back to it if you need. Right, so the next thing you do is, because we did only one bit, got to ask ourselves how to represent multiple bits. And that's where this comes. The other reason I use tech. Anyone here ever seen a tensor product before? Yes? Yeah, you're an engineer, we get it. All right. I guess I'll work down here. So the idea of the tensor product is I take the vector on the left, and for each component, I scale the vector on the right, and then just kind of add it to this really long list. So if this has like n things and this has m things, this should be an n. I am bad. All right. Then I'll have n times m things here in like a long column, right? So here I had 2 things, got 4 things. 2 things, 3 things, got 6. Anyone want to? Anyone have any other? I don't know. Yes.
Would the one on the bottom be 0, 1, 0, and then 0?
Wait, let me think about that.
Yeah.
Yeah. 0, 1, 0, 0. Yes. It is 0, 1, 0, 0. Well, since she just blurted it out, does everybody else follow that? Because I know like 3 or 4 of you did at least. If everyone's good with that, I'll just go to the next thing.
Can you explain how you got that?
Oh, sure, I'll just write it out. So 0, 1. Unless, Sarah, you want to get up and write it down.
Sure, you want me to?
You want to?
It's a lucky guess, so I don't know if my method's right.
Audience engagement.
Tensor multiplication is basically what you wish matrix multiplication
If you put it in your graphing calculator.
False.
Yes.
No, I agree with that.
I like linear optimism. I like linear operator composition. I don't know about you, man.
Heman likes paying us
Next slide. But they're for multiple bits. Do you want to get up and write it out, Sarah?
Sure.
Yeah, I get to sit.
I
I
can't
need pizza.
guarantee if the pattern I found is right, though.
Honestly, if you found a pattern, that's probably right, because there is a pattern.
There's like one pattern that you couldn't find.
So then I'm just like 1 times 0, 1 times 1, 0 times 0, 0 times 1.
No, that's exactly what the definition is.
That's what I guessed.
I mean, that's what's that roughly. I didn't even get to eat pizza. Damn. My pizza. You can take a slice if you want, because I didn't need 3.
Everybody, pay attention.
All right, yeah. So as Sarah just brilliantly wrote out, it's this, right? Everyone follows how she got this, or do you want me to write like another intermediate step? You good? All right, and then that just becomes that, because zeros and ones are easy. Cool. So now let's actually use these tensors for something, right, Kevin? So this is how a tensor is used. So if I have a 1 bit and a 0 bit sort of sitting next to each other in like a number or a register or whatever, I just tensor them to get the vector representation of that number. So that's how this whole thing works. Just a slight comment here. The whole comma is me simplifying notation. I don't know if like other people doing it use it. It's just easier for me that way, because otherwise it looks like a 10 and I'll get all up in my head. So anyone have any concerns with this one? Or yeah?
Why is it just one column instead of like a 2x2 matrix and like that example, for example?
So I mean, okay, let me go back to the definition, right? So how would you want it to be a 2x2 matrix, I guess, is a question.
Like where it says, because wait, is it isn't it just like matrix multiplication?
Nope. So what I'm going to do is I'm going to take this 0, 1 vector, right? And I'm going to scale it by 1 here. 1 here. And then for the next like 2 components of my vector, I'm going to scale it by a 0. And that's how I get this thing. And that's how I get a 4 by 1. Does that make sense?
Yeah.
Right. Yeah, because like this definition is also just really bad notation, right? Because like these vectors get like concatenated or something. Cool. Any other questions? So the point here is I can represent really long bit sequences in really long vectors. The other important thing is the Dirac notation mnemonic still works out. So because this is the binary representation for 4, I just have a 1 in array position 4 if I think of this as an array. So that's the whole like Dirac notation trick and why I guess some people care about it.
Wait, so you said it represents 4 because it's in the array position 4, or is it?
Yeah, I mean this is sort of hand wavy. I think that's why Ez is like giving me a frown. But for quantum computers, yes, I'll leave it at that. For the current application. Any other questions, comments, concerns?
What order do you multiply that in?
This one? It's associative. Yeah. So any order works here. That's a good point. And if you believe, yeah, okay, whatever. Actually, it's not commutative because here we multiplied these to get this guy. Here we're multiplying them in the other order and we're getting something different. Just a comment there. We good with this? So now we have multiple bits and they're vectors. Okay. So this is the first binary bit operator. So it takes 2 arguments in and changes the 2 arguments based on a rule. So this one, what it does is it's called a conditional not, and what it does is if the first bit is 1, it'll flip the other bit. Otherwise, it will do nothing. Does this make sense? Yes? By magic and voodoo, the matrix for it just happens to look like this. So if I take any 2 bits, which will be a vector of 4 things after I do the tensor product, and I multiply it by this matrix, I'll get another vector that represents the thing I want, basically. And then I'll sort of have to do this like decomposition of the tensor product, but the Dirac notation mnemonic just makes that easy, so we can do that, right? So, and then once I undo the tensor product to write it out, then I can get what each bit was supposed to be and then show you that it works. So if you follow this example, right, here I have the 1-bit set and the 0-bit off. So the bit I'm conditioning on is the first one. That's sort of a convention that people have. And so because this bit is set, I'm going to be flipping this one. So what I expect to get out is a 1, 1. Yes? And
Where's the 1, 1?
1, 1's there at the end. But first I'm going to cheat a lot because I am too lazy to do actual tensor products. So this is just the binary representation of a 2, which is why I put a 2 there. And then I look at array, so because it's a binary representation of a 2, using the mnemonic, I know that I'm going to have a 1 in array position 2. So that's what that vector is going to end up looking like. And then when I do the matrix vector product, I get this vector. Does everybody follow that? I don't know. Yes?
Sorry, is that tensor? For the 2 and the C?
No, this is matrix vector multiplication, because this ket becomes a vector. It's also called a ket. Yeah, so I get out this vector. Then I can use the mnemonic again because I'm lazy, and I know that's a 3 because the third position is the only one. And then because of that, I look at the binary representation, I get 1, 1. So
Is there a specific rule that the C vector follows, or is it different for any n being the number of elements in our tensor product? Is it different for any n?
what do you mean by C vector? Do you mean the matrix?
In this case, our C vector has like whatever, 1 0 0 0 1 0 0 whatever. If let's say our tensor product was just 1 and 0, right? So the 0 bit.
Yeah.
What would our C look like in that case? Is there a rule where we can get the C vector, or?
It's pretty much just the mnemonic, right? So if you look at a 0-bit, so you're taking a 0-bit and like another 0-bit, or do you want a 1-bit?
Any of those, whichever one.
All right, I'm going to do 0, 0, right?
Okay.
This is also the binary representation of a 0.
Yeah.
I guess the important thing to note here is because I had 2 bits here, I will end up with 4 things instead of the normal 2. So I'll represent 0 like this.
Okay.
In general, if you have like a tensor product of k things, k or k bits is a 2 to the k dimensional vector. So like that's sort of how this is a 4-dimensional vector, and I guess that's a problem, right? The mnemonic gets rid of that, but if we just remember it as we're doing our math, it'll work out.
So if you had C and then 1 comma 1, when you do this C naught on it, it wouldn't change the second one.
No, it would change the second one because the one,
1, 0?
because yeah. So
Okay.
so yeah, if we, I guess the point is this works backwards. Yeah, funny comment. C is its own inverse.
1, comma 1 would just give 1, comma 0.
What?
1, comma 1 would just give C 1, comma 0 after.
Yeah.
Like,
Right. So you just read this way and you get that. It works that way. Good. All right.
Wait, I have a quick question. Oh, do you want to go first?
Oh no, you go first.
Okay. Is there a way to get the final answer, which is like the 3 or the 1, 1, without doing the matrix multiplication?
I mean, just knowing how C naught works, right?
Okay.
Because you leave the first bit alone and flip the second one. I'm just kind of doing this to show you that this is indeed the matrix. The matrices get more important in quantum, but like before quantum, you don't really need them because classical computers don't do them. Yeah.
Oh, so this is just an example, and then later on, like we don't care about the matrix multiplication part. We just flip it in our heads and then add things up.
Other way. This is an example of something you can do without a matrix, but quantum operators, you do need the matrix.
So then, how do you expand the C to be like bigger? Because I suspect you'll have more bits later.
You don't, right? Because C is defined on like how many bits it's operating on.
Okay.
So like
Yeah, so
it'll always be
how
4
do
by
you-
4.
Oh, it'll always be 4 by 4.
Right, because it'll take in 2 bits and give you 2 bits out.
Oh, so you can't work with anything more than 2 bits.
You can't apply C to anything more than 2 bits. I mean,
Okay.
you can cheat and like stick an identity matrix here and then it'll all work out if you really want. But like it's not sort of defined by people yet because this is just sort of how C is used.
How much can you do with 2 bits though?
Yeah, and we only got 5 to work with nowadays. Don't worry about it. So half of what you can normally do, you know, give or take. Questions, comments, concerns? You good? All right, I'll go on. So yeah, now we can mess with qubits, which gives me the wonderful opportunity to actually draw a circle here. That's a circle. So that's essentially what happens, right? So the classical bits are just these 2 points on a circle. And all the qubits that technically exist are any point along the circle. If you're like somewhere out here along the circle, you're in superposition because you're halfway between a 0 and a 1. And the sort of intuitive idea is these distances give you the probability of being measured to one or the other. So if you're right in the middle, you're 50-50. A square root magically comes in because of the way magnitudes work. So it's like, it's the square root of the probability is the component in the vector. But that's like, exactly, right? Exactly, right? What? That was beautiful, all right.
So what's the qubit probability of that happening?
Which one?
Her screaming at the right time.
We don't have enough qubits to do that yet.
Oh.
Modeling Saran, that's hard.
What's the set C? What does the set C mean? Just the points on the unit circle?
No, C is the complex numbers. So actually what I'm showing you here is a complete and utter lie because you take out another copy of these for the imaginary axes and then you have everything you can do.
Okay.
Yeah, it's so qubits technically are 4-dimensional, and there are operators that exist that will move you in the imaginary dimensions too, but like they're really hard to draw and harder still to work with, so I'm not going to. So yeah, that's an important point. So A and B are complex numbers. So when I'm taking this absolute value, I'm like taking what they call the modulus, which is like I don't know. Do people know? Do people care about the complex numbers? Otherwise, I'm going to pretend they're real. What? Do you care?
Wait, what do you mean by complex number modulus?
Norm.
Oh.
Yeah.
Wait, what?
I don't know what word you know it as. So
Wait, what?
He normalizes it.
yeah.
Oh, okay.
No. So yeah, this is the complex number norm. If you think of them as complex numbers, if you think of them as real numbers, they're absolute values.
Okay, how is like inner product with complex numbers defined though? Or like how's norm defined?
You multiply by the conjugate.
No, defined.
Or you could just write out the real and the imaginary axis and then just do Euclidean.
So just the real squared.
Yeah, you can do that. It's allowed.
Are you saying by like turning like the complex by like turning the complex into like real that it's like when you deal with relating it to something that we do for like 3-dimension, like if you do like say the distance from the center of a sphere, it's like some distance, but then you flatten it out using like x, y, like alright, it's this distance, so whatever it's equal. Is that what you're doing with a complex to real?
It's a 4-dimensional sphere.
I can't do 4-dimensional meaning like the x, y.
So there's an x, y, and then there's like a z, w, like axes, right?
They're all together.
Because I mean, this is going to be 2 dimensionals over the reals. This is going to be 2 dimensions over the reals, so like 4 dimensions in what you're used to dealing with. But what I'm saying is, for the purposes of this talk, I'm just going to look at one of the circles in this 4-dimensional thing, which are the 2 real axes.
Planes.
Yeah, one of the planes. So circular cross sections.
Does that mean we're working with conics?
No. Fortunately, no.
For that fourth bullet point, is that the tensor product or is that the cross product?
It's tensor. So there's like a little bit of sort of abuse here because
Yeah.
I go up in dimensions here and I don't here. But my entire point is you're not going to leave the higher dimensional unit circle by just taking 2 things on the unit circle in the lower dimensions.
Is that wait, remind me, is that a dot product or on the other side or is that a
These are numbers, so I can just multiply.
oh.
Yeah.
Okay.
So basically what I'm saying is like as I add more bits, everything still lives on a unit sphere in how many ever dimensions I need.
Okay.
How do you go from greater to smaller dimensions?
Great.
Like your tensor thingy. Like in the fourth bullet. How do you
You don't. What you can do is, I mean, you'd only really need to do that if you had an operator that acted on only like a few of the bits you cared about. And the trick is you basically stick an identity matrix everywhere else. So like, say I only cared about like a bit here, like I only cared about bits A and B here, and I had like some other bits that I don't really care about here, right? In some like long thing that only theoretically exists. Oh boy.
It went to 0.
No, it fell asleep because I'm boring. Right? So what I can do is put my 2-bit operator here, which is a 4x4 matrix, and then I can just stick ones along the diagonal so that it doesn't really touch the other bits. That's sort of how I can look at it mathematically. I mean, circuit-wise, it's just don't do the operator to the other things, because that's what identity is.
So you have arbitrary dimensions for arbitrary dimensions for any bits, and this is just the ones you care about.
Yep. All right, we're back. All right. So yeah, you can see this as a unit circle. For our purposes, I'm not going to leave this unit circle. So if complex numbers scare you, don't worry, they scare me too. We're going to live here. And the other one is just saying, hey, as I add more bits, I live on a unit circle still. So the whole unit circliness is kept. All right.
Do you ever cross over from complex to like, does the same set of like rules kind of like apply between real and like the same kind of rules apply with complex? And is there something funny when you do from real to complex and complex to real?
When you say rules, what do you mean?
Whatever you're doing there.
What? Matrix multiplication stuff?
No, like with the circle, with the plane. Like how you operate there.
If I ever go into complex and then do stuff and then come back out, weird stuff might have happened. But I won't ever do that, so we're okay. There are, if you look at like IBM's kit for this whole thing, there are operators that do that. I haven't really read up on how they work because I'm not going to venture into those unknowns. But they exist. I'm sure they have some application to quantum computing too because they exist. But yeah. I mean, I can try drawing out some stuff a little later on. But this is how you go from what I was showing you with classical bits to qubits. So everything I said beforehand still holds. Like identity can still be thought of as this on a bit. Negation is still this. Now what do I do? Right. But now this is the extra special thing I can do. And because of physics measurability and like other concerns, this is pretty much the only thing I can do while I'm still on this circle. So what that essentially does, if people really know like linear algebra, maybe you can shout it out.
Rotation.
Okay. Close.
5-degree reflection.
Oh, it says it there. Yeah, cool.
What's a rotation? Oh, no.
No, it's not exactly. I don't know. I was thinking about like group theory when I was doing it because I kind of saw that, but then I was like, nah.
Can you do a rotation though?
Yeah, he did.
Can you do a rotation?
Yeah, working with what we've got.
You can kind of do a rotation. You wouldn't really want to. Actually, you can't because the operations have to be self-inverse. It's like another sort of physics gotcha. So you can't do a rotation because it won't be self-inverse unless you do a 180-degree rotation. But that's a reflection. You can do it in quaternions. There's just like, I've just been told that in physics the operations have to be self-inverse. That was what they said earlier. It just doesn't come up that often.
Yeah, but with mathematics, they don't care what the physicists think.
Yeah, so I can do it in the math, but sometimes the theoretical framework is too big for the real world anyway.
Wait, all unit operations, or if you decompose it into two self-inverse operations, you can?
What? Oh, yeah, so if I can decompose it into self-inverse operations, I can.
Okay.
But I don't think I can get rotations out of that. Or not. Yeah, I won't be able to recover every rotation out of that. There would be like some sort of. You will. Okay, that's not true. Yeah, you will be able to. You just need like sort of an infinite set of like these sort of kind of matrices to be able to like reflect along like different lines.
Yeah.
But yeah. So if I take this line. Actually, yeah. So. If I take this line and reflect about it, that's what the Hadamard does. So this line is like a quarter of the way between, what is it, 20? Yeah, so this line's a quarter of the way to the 90 degrees. So it's like 22.5 or like pi over 8 if you like that one. But that's what it looks like. It looks like this sort of reflection. If you know your linear algebra really quickly, you can just kind of see that because that's what you get out of this. And yeah, it's also self-inverse, so if I take it again on something that I did it to, I can go back to a classical state and I'll be okay. And if I do it once, I land here, which is which is at 45. And okay, yes. And it has equal probability of going back down, up or down. So this is like what you were saying, where like now if I measured it, it can be either or, but like uniformly. Cool? Yeah, so you can make random numbers now. I think, yeah. So the two big operators we have so far are on the one bit level are flipping and Hadamard. So bit flip is, I go from here to here. So let me just, draw, right? So I can go from here to here. If I bit flip in perfect superposition, I land right back to where I started. So that's pretty much the only arrow I can draw on what I have. But if I were to draw all 8, I'd kind of recover this whole thing. Right? And you can sort of see how this reflection is what I said it was, which is like, if you look at the quarter waypoint here, it's just like reflecting over that line.
Why'd you do this by 2.5 again?
What? That's this angle, which is like a quarter of the way to 90.
I thought perfect superposition was the 45 degree.
Right, so you reflect over 22.5 to go to 45.
Oh, okay.
Yeah.
When you say perfect, does that mean that there are some cases where you perform this operation but it doesn't cooperate and it doesn't do it the full way?
Unfortunately, yes.
Okay.
But like, we're theoreticians. We're going to pretend that the world is like good for us right now.
Oh, okay.
So you can't make a perfect Hadamard gate.
Yeah, not yet. you can make it close enough, which is why like when, oh you weren't, yeah, which is why like most of the algorithms have like error bounds in them right now, because we're not yet that good at quantum. Oh, I forgot to talk about Turing. All right, so here's where I'll sort of transition. What time is it, incidentally?
7:53.
All right, so I'm just gonna show you like one or two quick things, I guess. But so IBM has this thing called QuizKit, which is like their quantum API kit, and what it does, essentially, it's actually really cute. I'll like click to it in a few seconds, but it has an assembly language that you can run, and you can like locally simulate on your computer, or you can ask IBM to run it on their quantum computers for like some amount of money. But more importantly, let me open up the Firefox tab. Hey. So more importantly, they have this. If you Google the right thing, you'll get here. I don't know. I have a link to it in my presentation. I guess I should have put it in the Facebook event or something. But
I can put the link in the Facebook event.
yeah, so if you guys want to pull it up on your own laptop, feel free to do that. Wait, you have access to the PDF, yeah, so you'll get the link in a few seconds.
Turn on dark mode
No, I must blind myself.
on the bottom right.
I know, but I want to blind myself. Let me just sign in real quick, and then I can run a couple quick things. Oh, wait, this is bad. All right. Oh, cheat time. Boop. By the power of cookies, I'm signed in. All right. So the best example is like the dumbest example, which is I can just chuck in a Hadamard gate somewhere. So wait, firstly, can people see this?
So do you write the code like you write Scratch?
I like to think of it as music, because it's like 5, and you know, like now I'm playing a high F on the Hadamard instrument. I don't know. It's like, right? I can put like a nice little treble clef. Nice one. Right, but anyway. So what was I going to say here? Yeah, so the notation here is like, as I go left to right, I'm going to be applying operators. These are my 5 qubits, which is the most humanity can ever do consistently. There are a few experiments on doing more, but this is the one that is most supported right now. And these zeros means I'm initializing them all to the 0 bit. And then I have a bunch of gates, right? So these are the Hadamard and the flip that I was talking about. There's also an identity gate. I don't know why they have it, but it's there. You can ask it for help on all these gates, which I did once, and you can actually get the matrices they are. So if you ever want to do this math on your own, for whatever reason, you can play with that. Maybe then you can see how going into complex will do things. I think the T and T, like upper cross, do complex rotations. So if you want to look at them. This one's a C naught. I can apply it I'll apply it later maybe.
What are the S ones?
I don't remember. I think they're also some different, they're different complex rotations because I have 2 eyes. And then of course this one is the important one, which is let's get back to the real world and measure it. So I'm gonna just stick on a measure here, right? So this is that no-no, right? Because it's in perfect superposition, and then I'm gonna measure it. Because running it actually takes time and experiment units, I'm going to just simulate it. I actually submitted a job for running earlier, and in like half an hour it hadn't yet run, so then I gave up. But if I simulate, I'll just call it high, because I'm good at documentation. See, even they call it scores, right? So here you can see the ugly assembly language, which isn't actually that ugly if you're used to x86. No addressing modes because we don't have addresses yet. So it's not that bad. And then yeah, if you see the results, because it's a simulator, it's not going to be like that exciting, but it's almost 50-50 zeros and ones. And if I keep running it, you'll get different numbers, because this one's kind of far from 50-50, but I guess if I ran it again, you'd get different numbers. So that's that basic experiment. I guess another thing, so yeah. Yeah, it's almost Qasim, I know. I kept typing Qasim when I was writing it out. I was like, damn it, it's not Qasim.
Open custom.
Open Qasim. Yeah.
Awesome.
Yeah, man. I guess another thing that might be worth demoing is that if I Hadamard twice, I'm going to get some. Oh, it's after the measurement. Okay, I see how it is. Let's just do that. So I think, yeah, after I measure, because the whole quantumness like dies, it's dead. So I can't do it again. But if I Hadamard twice, I'm just going to get whatever I started with. So you'll just see 0.50s and 0.51s if I'm correct, because it samples with half ones and half zeros when it runs the experiment. Tony, I think, or never mind. Oh no, I'm dumb. I started the bit at 0. Yeah, so the Hadamard just canceled itself out. Cool? Yeah, I guess I'll stop here because it's 1 minute left, so good timing. Anyone have any questions?
When you do the measurement, do you have to worry about like looking at your actual thing whether that like alters what's going on?
Like Heisenberg uncertainty?
Yeah.
I think so, but I'm not certain on that myself. I have some uncertainty. It's the Heman Gandhi uncertainty of not knowing physics. Anyone else?